Automatic Addison.
In this tutorial, you will learn how to customize your robot with parameters in C++. Parameters are important for creating flexible and dynamic robot software. By the end of this tutorial, you will be able to use parameters to make your robot move like this. You'll learn how to define, access, and use parameters within your nodes, enabling you to customize your robot's behavior without altering its code. Join me as we dive into the essentials of parameters, setting the foundation for more complex robotics applications. Here are some real-world examples of how ROS2 parameters can be used in robotics applications. First, joint limits and velocities. Parameters can be used to define the safe operating range, the minimum and maximum for each joint of the arm in terms of angles or positions. Second, payload capacity. This parameter defines the maximum weight the arm can safely carry while maintaining stability and avoiding damage to its motors or gears. Number three, path planning parameters. These parameters influence how the arm plans each trajectory to reach a target point. And then finally, end effector calibration. Parameters can store calibration data for the gripper or any tool attached to the end of the arm. Pretty much any variable that applies to your robot can be declared as a parameter in ROS2. Parameters are used to configure nodes at startup and during runtime without changing the code. Remember, a ROS2 node is a mini program written in either Python or C++ that performs a specific task within a robotics system. Let's start by creating a ROS2 node that declares 4 parameters. And let's just run through these parameters now. The first parameter is the robot name, which represents the name of the robot, just a string, simple string. Second parameter we will use is a robot ID integer. So this is consider it the unique ID number for the robot. The third one you see is the target linear velocity, which is a floating point value. And this is how fast we want the robot to move forward or sideways in meters per second. And then the last parameter, the fourth parameter, which we will declare is the target angular velocity, also a floating point value. And this sets how fast we want the robot to rotate in radians per second. So let's talk about the node setup. The node will include a function that executes anytime one of the parameters changes. The node will also publish velocity messages, which is a geometry message, twist stamp message, to the Mecanum Drive Controller CMD-vel topic that has as inputs the target linear velocity in the X and Y direction and the target angular velocity rotation around the Z-axis. So these are the parameters. So this publisher publishes a new velocity message at a rate of 2 hertz, so roughly 2 times per second. And the default velocity is 0 meters per second for linear velocities and 0 radians per second for angular velocity. Now, because we're parameterizing the velocity values, you can change the linear and angular velocity parameters at runtime, and the values will automatically update. Okay, let's get to it. Let's open a new terminal window right now, and let's go to the CD ROS2 Workspace source Yaboom ROS master, Yaboom ROS master system test, and source. Okay, we're in here now, and let's create a new file called Mecanum parameters node.cpp. Touch Mecanum parameters node.cpp. Okay, and let's open it. All right, so this is a blank file right here. And I've got the code that I download off of GitHub. Let's find it here. Control A. Let's go over here to get it. Okay, and here's the code. Full code is on GitHub under the Yaboom ROS master systems folder, SRC folder inside of that. So you can find it in my Yaboom ROS master GitHub repository. And what does this program do? What does it do? Well, this implements the whole ROS2 node that I described in that previous slide. So we're declaring the parameters for the Mecanum wheel robot. Got all the parameters here, our robot name, our ID, target linear velocity, and the angular velocity. So very cool. Let's just change the date. Today is May 17th, 2025. And I really like to structure my programs like this, ROS2 nodes. Not everyone does it like this, but this keeps things very organized. So we start off with the file name, have a little brief description of what the node does. So this ROS2 node demonstrates how to declare parameters and publish velocity messages. Then we've got a more detailed description below that of what the node actually does. Then, as all ROS2 nodes that are publishers of subscribers, you want to list what the topics are right here that the node subscribes to. In this case, none. We're just publishing right here, velocity command for the robot. All right. And then we've got different parameters right here, which I described earlier. Okay, it makes it nice and easy. So, you know, if I ever get run over by a car, somebody can easily come here and take a look at the code and see what this code is doing without having to dive into the weeds. So here are include statements. We definitely need the geometry message twist stamped header file because we're dealing with velocity messages. And we've got our RCL interfaces that help us deal with ROS2 parameters. Okay, now we've got our comment right here explaining the Mecanum parameters class. This is where we're declaring the Mecanum parameters node, and we're inheriting the node library, but this is our class. And this inheritance makes it a ROS2 node. We name it. Here's where we describe the parameters. This is very useful to describe what each parameter means. So you can be able to see that at runtime. Here's where we declare some default values for the parameters. And for robot name, I'm going to default it automatic Addison bot. Robot ID, let's make that 1. Got our target linear velocity, x and 1. Started off at 0. We don't want our robot running away when we start up the robot. Got our angular velocity in radians per second. Here's our callback function. This callback function will trigger and execute, okay, anytime there is a parameter change. Then we create our velocity publisher to publish the velocity commands to the appropriate topic that can then be read into ROS2 and transferred over into Gazebo using the ROS-GZ bridge, and then executed in Gazebo so our robot can move. Now we've got our callback function down here, the method that actually runs when there is a change in one of those parameters above. And when that happens, we actually check in this code down here, which parameter changed? Which parameter changed? Okay, if it's the robot name, I want you to get the new name and I want you to change it. And then spit out something to the logs, which tell us, oh, we just changed the robot name. And so forth with all the other parameters. It's long if, else if, else if, else if, else if, all the way down to else. Otherwise, if there's some weird parameter, which has actually never been declared, we also indicate that as well down here. We catch it down here in this else piece of this if else if statement, and then return the result. Then we want to publish velocity messages. Here is our workhorse velocity method that's responsible for creating the velocity message, okay? Getting the current time with this clock now, the frame, okay, the frame for the velocity message. In this case, we want the base link. That's the base link of the Yaboom ROS Master robot. Then we got the target linear and angular velocity. And publish. And then we have a timer. So we're going to be publishing periodically. And here's our typical main method where we connect to ROS on this line, set up the node, spin it, and then shut it down when we're ready. And we press Control C and then return 0 to round it out. So that is our code. This is our main node. Let's close everything out. Okay, now let's edit our package.xml file to update the package dependencies. So we're going to go here, cd ... Let's go to get it, package.xml. Here we go. Here we go, here we go, here we go. And we need to add a line because remember we're dealing with parameters now. So let's add a line down here. I like to keep things in alphabetical order. Depend and RCL interfaces. Depend. Save. Save the file. Okay, and close it. Now we need to update CMakeLists.txt. Okay, let's update our CMakeLists.txt. We need to make sure to add our new node. So let's do get it, CMakeList.txt. And let's see what we need to do. We need to first start dependencies. Let's start at the top here. CLCPP, action, geometry messages, we're good, stood messages. And let's add another line under stood messages. Let's put this line under here, our new dependency, RCL interfaces, which is the library that handles parameters. Okay, and let's see, we've got the square mecanum controller. Mecanum parameters node is the name, so let's add it. Let's add it down here under line 21. I'm going to add this code. Okay. Add it right there. Add executable, mecanum parameters node, source, mecanum parameters node.cpp. And once you've done that, you also need to add the dependencies. Let's do that down here. That's this block right here from line 33 through 39, mecanum parameters node, and then it's going to depend on RCL CPP, geometry messages, stood messages, and RCL interfaces. Okay, once you've done that, we need to go down here and square mecanum controller. Right underneath that, we need to install the executables. Mecanum parameters node. Save. And that's it. Save it, close it. Let's open a new terminal. Okay, we're going to go CD, ROS2, Workspace, clear, do colcon build, and source the bash. Okay, colcon build and source our bash RC. If you've been following my tutorials, this should all work. It both builds the workspace as well as sources the ROS distribution in the workspace. So I've put all the typical, so typically people would just source the workspace in ROS2. They do it manually through the terminal, but I put it in, I'll show you here. It'd be easier than explaining. I actually put that in the bash RC file, which I'll show you in a second. Okay, let's go to get it. .bash rc. So this line where we source our ROS setup, ROS workspace, and then we also tell our terminal that we're using ROS2 Jazzy. People would typically do all of this manually, but I don't. I just stick it all in the bash RC. Things that are repetitive, commands that you run again and again and again, just put it in the bash RC, folks. Put in the bash RC. It'll make your life easier. By the way, I also have a alias called build, which CDs to the workspace, runs a colcon build, and sources a bash RC. So let's just show you that again right here. There's my alias. So I'm going to clear, and let's just run the build to build everything again. Okay, looking good. So now let's shut this off. Now it's time to launch the robot. Let's open up a terminal window. Going to use the alias to launch the robot. If you've been following along with me, you'll know that alias runs a bash script which launches the robot in RViz and Gazebo, and as well as setting the camera frame perspective automatically. So go take a look at my older tutorials if you want to see what that means. Let it come up, let it take its time. You know everything's good when the logs in the terminal stop. And the robot looks fine in RViz and Gazebo. Everything is up. Okay, now let's go over to a terminal window and let's launch our node. ROS2 run yaboom ROS master system tests. Let's do mechanic parameters node. Press enter. Okay, we shouldn't expect anything to happen because our default velocities are 0. Nothing happened. Now let's open a terminal window, and what are the currently active nodes? ROS2 node list. There are the active nodes. This is what you should see right now. We can see our beautiful mechanic parameters node right there. There it is. All right, and how do we list the parameters? ROS2 param list. This lists all the parameters for all nodes in the system. Takes some time, so it's pretty big, and you can see it's massive, massive. Each node, it lists the parameters. And look right here. Got our mechanic parameters node, and we can see our different parameters here, right here. It's clear. Let's retrieve the value of a specific parameter for a node. So to do that, you do ROS2 param get mechanic parameters node. And what about robot name? And why are we freezing? Robot name. Get it. Okay, it's automatic Addison bot as we expected, string value. How about the robot ID? Let's check that one. Robot ID. Should expect 1. Yep, 1. How about the target linear velocity in the X direction? Target linear velocity X. 0. Exactly as we expect. Let's check the Y. Okay, 0 as well. How about the angular velocity? Target angular velocity. Velocity. 0. Okay, very cool. Now, how do we double check? Let's see. Let's try changing. Let's try changing the name of the robot. How do we do that? So changing parameters. So do ROS2 param set mechanic parameters node robot name. Okay, and let's see, ROS2 param set mechanic parameters node. Okay, and then robot name parameter, and we want to change the name to new automatic Addison bot. New automatic Addison bot. Enter. Set parameters successful. Let's double check the new name. Let's do the up button. Up, 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 up. Robot name, ROS2 param get mechanic parameters node robot name. See if it got the new name. It did. New automatic Addison bot. Okay. Okay, let's minimize this screen so we can see everything. Like in Gazebo. Okay, and what I'm going to do now is let's make the robot rotate counterclockwise. How do we do that? We have to change the angular velocity. So let's do that now. We'll do ROS2 param set mecanum parameters node target angular velocity minus 0.5. So ROS2 param set mecanum parameters node target angular velocity and then minus 0.5. Remember, folks, with angular velocity, positive is counterclockwise and negative is clockwise. So we want to rotate clockwise around the z-axis. This is the yaw rate, minus 0.5 radians per second. Press enter. Okay, and now if we go close in here, you can see the robot is rotating clockwise. Pretty cool. Now let's go over here and let's do ROS2 param get. Let's do Control C. ROS2 param get mecanum parameters node target angular velocity minus 0.5 radians per second. Pretty cool. Now let's go and do Control C to close everything out. Now I'm going to show you how to create a YAML file, okay, or just a text file, which will contain our desired parameters. We will then import that YAML file into a launch file and launch the robot in Gazebo. So let's do that now. So this is much easier than, it's actually more flexible than doing all the hard coding that we did in our program, hard coding, because we've got defaults that are set inside the mecanum parameters node. And if we want to change it, we're doing it by the command line. But yeah, how do we launch our node so that it has our desired parameters, you know, that it pulls from a YAML, a text file? Let's do that now. So we're going to go to CD ROS2 source Yaboom ROS master systems tests. Let's see, we got make dir launch. Okay, let's CD launch. Okay, and let's create a new file. Let's do touch mecanum parameters .launch.py. Let's open it, get it, mecanum. Blank file for now. I've downloaded everything from GitHub repository. You can find this launch file there. Let's check it out. Launch. Let's open with get it. Okay, I'm going to Control A from what I downloaded from the repo. Let's put it in here. Again, you can just use my GitHub repo, fork it, you know, and run all this. But I think it's important for your learning to understand how you create all this stuff from scratch, because in the real world, you're going to have a different robot. If you work for a company or if you're at a school, you're going to need to do this all from scratch. And here is our launch file right here. So this launches the mecanum parameters node with configurable parameters in a YAML file. So let's just walk through it. So up top, I've got my description of the launch file. I have my imports right here, my different libraries that make the launch file possible. Here's where I define the package where my mecanum parameters node exists. In this case, it's the Yaboom ROS master system test package. Then we have to put our path to the YAML file. We'll create that in the next step. We find the package stored in the variable, the path to the package in a variable. Have a launch configuration variable, mecanum params, where we can actually provide the path to the YAML file in a launch command when we run this launch file. And we put the node right here. We declare the node right here, and we launch it down in here as part of an action, launch description action down below. So that's it. That's all it does. Save it. Okay, so that's that. Let's now create the YAML file. cd ... clear. Okay, let's make dir config, cd config, and let's create our YAML file. Let's call it, let's do a get it, mecanum parameters.yaml. Okay, and let's go back over here. GitHub, this is what we had before. Going to Control A, all of that, Control C, and let's go back to get it. Paste that into our YAML. So you can see mecanum parameters.yaml. And here is where we have set our own values for the different parameters in the mecanum parameters node. Okay, and this will be loaded at launch time. We launch the launch file. So let's close that out. Save it and close. Okay, because we've just added 2 new folders, we need to edit our CMakeLists.txt. Let's do that now. Get it, CMakeLists.txt. And let's update that puppy now. Let's go. Where do we edit? Where do we edit? So I like to put that under the find package. Okay, and let's add this block of code right here. So here is where we set the directories that we want CMake to know. In this case, we want config and launch. So add this block of code right here from 16 to 20. Pause it, add it, take your time. All right, when you save it, close it out. Okay, let's clear, build. Alrighty, we built, everything built fine. Okay, now let's open up this terminal and let's launch the robot again. So in this terminal, I'm going to do X3 to launch the whole gazebo simulation of the Yaboom ROS Master or X3 robot with RViz. Let it come up, take its time. Okay, and what did we set? Well, that's trying to come up. Let's go back to the ROS2 workspace source, Yaboom ROS Master systems test. And what did we set? The default velocity, angular. Okay, so 0.23 radians per second. So what should we expect when we actually launch the launch file that we just created? We should expect the robot to rotate counterclockwise 0.23 radians per second as soon as we launch the launch file. Let's see if we get that. So robot stationary right now, not moving. Let's open a terminal. Let's keep this below. Okay, here's our terminal window, clean terminal on the bottom. And let's launch. ROS2 launch Yaboom ROS Master systems tests and the mecanum parameters .launch.py. Press enter. Everything looking good. Is the robot rotating clockwise? Sorry, counterclockwise? And it is. It is. Rotating counterclockwise, just as we expected. So let's go into the terminal and let's check the velocity values. ROS2 topic echo mecanum drive controller cmd vel. Enter. And you can see right here when we did an echo on the velocity that we're getting 0.23 radians per second, just as we should expect. That's it for this tutorial. Thank you for following this tutorial. Keep building.